Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure today to introduce Naomi.
Yes.
Who is here from Tokyo Institute of Technology and is interviewing for a postdoc position in the concurrency group. He's going to tell us about, I think it's your PhD research?
Yes.
Part of your PhD research on fault localization in large-scale computing systems.
Thank you. So, thanks for the introduction. My name is Naoya Maruyama from Tokyo Institute of Technology. Today I'm going to talk about my work, my part of the thesis work on fault localization for the large-scale computing systems. My specific area of focus is high-performance computing, like supercomputers and grid computing environments. And for that, so to begin with this talk, I first sketched out some large-scale failures in real-world environments. So one of the recent failures in the computer system is happened in Japan, the Tokyo area. So we had most of the stations in the Tokyo area had automated gates, much like the gates in this building for the entrance. And several months ago, it stopped working in the morning without any manifestation before that. The system was working for a long time, maybe a couple of years, but just stopped working. And the people can't get into the station because of the trouble. So it turns out it's just the reason of the trouble was some very subtle or miscoding of string manipulation. And but it takes about 1 week to determine the reason of the trouble. That's one of the recent failure in the real world environment. And it just takes time to understand why it wasn't working, what's the reason of the failure. So that's the motivation of our work. And so here is an example of the failures in the distributed environment. So we have infrastructure of just a collection of clusters distributed over Japanese universities. It currently has 6 sites to host the clusters in Japanese universities. And one of the users tried to run a power program, MPI power program. It uses he used a popular MPI implementation called MPI-C8, and but he had some trouble. MPI-C8 comes with a job manager called MPD. It manages power application, and it starts power process on each node of the power machines. And it works without no problem on the single computer, on a single supercomputer or a single cluster. But when he uses it with 3 clusters distributed in universities, apparently the MPD daemon has stopped working before launching processes. But it sometimes works, but oftentimes it doesn't work. And actually, the probability of the failure increase if he increase the number of nodes or number of sites to use. And he's actually he's a friend of mine. He's a graduate student of another university, he has a very good talent to diagnose the problem. So he changed some code in the daemon source code and tracks the reason of the program and identifies the cause. It turns out a very simple bug. It's just missing of checking to return value from the receive system calls. The program assumed it always receives some amount of bytes, but it's actually it was actually true in the tightly coupled environment because the latency is relatively very small. But when used with the distributed environments, it causes some problem. And the bug caused the system to close the network connections among the daemons, but doesn't terminate the system itself, or doesn't notify the user of the system what was going on. It just hangs up. So he inserted printf to the program and takes some long time to find the reason of this bug. So we want to automate his process of the debugging. We want to take the manual burden to a more automated process. So that's a motivating example. So the reason of the difficulty for the localization in our target environments like supercomputers and great environments, one of the reasons is scaling up. So this is a picture of the supercomputer that we have in our university. It is currently the fastest supercomputer in Japan. It's about 15th in the world. It has more than 600 nodes. Each has 16 CPU cores. So this is another much more large-scale machine is Lawrence Livermore National Laboratory's Virgin supercomputer. It has more than 6K nodes. So it simply increases the burden of the localization. You first need for the sequential program, you know the program caused the trouble. You just need to look at the sequential process, one single process. But in this environment, you need to work with this kind of large-scale number of processes and environments. Also, the grid computing, it uses a heterogeneous collection of machines distributed over the network, like a SETI form. Also, environment, as I said, called integer. It's as I said, it's a collection of distributed machines. It causes when you are using multiple sites or multiple clusters, you are also dealing with the time to localize the force is also increased because you need to look at the more complex situations. So that's one of the reasons. Another reason is the diversity in the current trend, current standard clusters. So typically, the supercomputer was manufactured by a single vendor. A single vendor creates hardware and operating systems and library for the scientific applications. But current typical configuration use standard Intel CPUs with Linux operating system and other various middlewares like Grovas or MPI. And even today, even has ZPUs for the specialized computing applications. So there's these kinds of diversity allows flexibility with relatively low cost compared to traditional single vendor machines. But because of the possible number of combination, it increases the chance of unexpected behavior. You can't predict what's the actual usage scenario from the when you are developing the software. It might be used for this hardware or might be used as a hardware. So the combination is much more larger compared to the traditional system configuration. So that makes the chance of the failure. So on these environments, the existing approach is just printf debugging. You insert the printf to program various locations of the program and rerun the system and then check the outputs of the printf. And then from the inside of the printf result, then might need to continue the iteration some time to get the actual result, actual cause of the failure. But this is too ad hoc, and it's not a practical solution for the current large-scale systems. Another approach is using power debuggers like Total View, or Microsoft's Visual Studio also provides power debugging for MPI programs, but it's hard to reproduce failures because of the it works for many programs, but for the non-deterministic bugs, it's hard to reproduce bugs with these kind of interactive debuggers. So our goal is to assisting localizing faults in these large-scale systems, and we want to automate as much as possible with the ability to reveal fine-grained information. Also, one of the important focuses is scalability with a large number of processes or nodes. So our approach in this particular work is to learn what's the standard behavior of the system. So we first to the process, we first inject a tracer to the processes. Then take a function called trace from the process, create a model that reflects the normal execution behavior. So we create a model while the system was working correctly. Then if something wrong happens, then we compare the model with the trace that we corrected when the system failed. So this is a general overview of our approach. Our current contributions are the sort of the model-based fault localization for large-scale computing systems. And also, we have demonstrated its effectiveness with the problem I just mentioned at the beginning of this talk, with an MPD problem. So our approach first corrected function called traces from each process, and then analyze the corrected data. We create a model, and then find the anomalies by comparing the standard behavior and failed behavior. So the first two steps can be automated, but the the next step is to report the result of our analysis to the developers or system administrators for further localization. So, and this second step is the main focus of this work. So let me first describe what the data collection looks like. We collect function call traces at each function call and return. We record function address and process ID and thread ID and timestamps with optional arguments for some specific system calls. So this, because we take function call level of information, we can do analysis of function level. So, for example, we can say a function x is have something strange behavior. Also, because we take all the call and return, we can do context-sensitive analysis. So, for example, we can say function x is strange when called from other function y. So that's a brief description of our data collection technique.
What do you mean by timestamp?
Timestamp is just in this case, it's a cycle counter of the processor. The time of the function call or return.
So this is happening on multiple sites, right? So if this is a distributed application, then there are nodes communicating with each other.
Yes.
So how are the timestamps on the different nodes correlated?
We don't use a timestamp correlation between remote nodes. We use the timestamp information for just inside the process.
Okay.
So we don't because we can't assume the cycle counters are correlated with the remote nodes. So, so our observation for modeling is these 2 points. So we use these heuristics for modeling. So one of the is if function is called most of the time, but it wasn't called when the system went wrong, it probably has something suspicious behavior. Also, if the function wasn't called when system was correcting normally, but it was actually called, it actually might be suspicious. So, for example, in Japan, we also had a system failure in the Tokyo Stock Exchange last week. And the reason of the trouble was some initialization code wasn't executed as some particular case. In that kind of trouble, we can, so that's kind of observation motivates our modeling technique. So to detect these kind of suspicious activities, we model of the execution by function calling probabilities. We first create a construct call trees of the functions, and then estimate the probability of each call from the corrected function call traces. So this is a simple example. We have just word traces here, and then we just count the number of calls. Then we annotate the function call trees by the estimated probability. So here we see 2 calls to F and also 2 calls to G. So we estimate the probability by 1.0. But for H, we only see a single call to H. So we estimate the probability by 0.5. So we do this for every function calls, every functions. that appeared in the code traces. So this is the basis of our modeling, but we do refinement to this modeling by two techniques. So the motivation for this refinement is if we know some part of the program has different characteristics with other part, then why not just give you different model to each part? So for example, if let's suppose we have some distributed file system. That system might consist of a daemon process on each node. So the daemon needs to contact to the front end, also might need to exchange information with other daemons and on the other nodes. So the code for communicating with the front end and the code for the exchanging information with other daemon probably has different properties, different characteristics. So we want to assign different model to each of these different characteristics part of the code. So that's example of these refinements. So we currently have two refinement techniques. One is a connection specific modeling that I will shortly introduce in the subsequent slides. Also another is the process law specific modeling, which I haven't included in these slides. So the second technique is to estimate the roles of a particular process in the distributed system. We do this by checking the how each process what network connection each process initializes at the beginning of the stage of the execution. If a particular process creates a connection to the front end and other daemons, we assume the process is we assign a model to the process. The another process also initializes the same set of connections with the first one. We assume they are the same. They are in the same class of processes in the distributed system. So that makes that is to differentiate front-end process and as a daemon process. Probably front-end system has many connections to many worker daemon processes. That has a different characteristics with other daemon process. So we detect such difference and then give you two different models to each class. The other is a connection specific. It's similar, but it's to differentiate the behavior of the intra-process. So for this refinement, we assume the architecture of software, of the target software. We assume the so-called event-driven system, event-driven architecture. It's a typical architecture of the most of the distributed system for HPC. So in that case, most of the typical system looks like this. So do some initialization at first, and then enter the infinite loop to check the connection of the incoming message and do something for the message, and then check another message for another connection. So we decompose this sequence of program to particular part of the execution units. So for example, in this case, we detect this organization of software of the program. Then we assign a model for each part of the system. So in this case, we first identify the main loop for the event handling. We assume, for that purpose, we assume the outermost loop is the main loop of the program. We detect the outermost loop by checking the corrected traces. Then we divide the trace at just before each call to receive system calls. We assume the calls correspond to message handling boundaries. Then we group the divided subtrace by the where the message comes from. We define the equivalence of the units by the whether it has the same call stacks to the connection that establish the connection. For example, if this message handler part of the code receives this connection, and another subtrace also receives some message from other connection. Both are established by the same call stacks. It means from the same sequence of the program with each other. Then we assume they are the same connections, and we create a single model to each connection, to the units. But if two units has connections that are established differently, we assign different units, so that we, from the call stacks, we estimate the characteristics of a particular connection. So that makes that is for creating a model for different behavior inside the process. For communicating with the front end, we assign this model, and for communicating with another daemon, we assign this model. So that makes the modeling more accurate.
So can I ask a question?
Sure.
So you're saying that at a call that's doing any network activity,
Mhm.
like a sender or receive,
Yeah.
you compute a signature for that based on the call stack?
Yes.
So if I have different call chains to the receive
Mhm.
or different calls chains to the send, I basically partition the send into buckets based on the call.
The call stacks to the, so if we have this receive get a message from this connection, and we examine how the connection was established. What's the call path to the establishment of the call stacks? We don't use the call stacks to each receive and send. We just looked at the system calls like connect and accept.
Oh, it's just on those two calls?
Yes.
Okay. So it's, I see. So that's why you say it's connection based. So when you
Yeah.
establish the connection, there might be different call stacks for different connections.
Right.
You
Yeah.
distinguish those.
Yes. So we do this by recording the descriptor number of each system call, each socket calls.
So you are recording in your system then every message send, every network. Are you also logging every network? Send, receive. Are you matching sends and receives?
No, we don't do matching for the remote machines. We just record the so for every function call, we records function address and timestamp, the process ID, and for system calls to socket interface, we also record particular arguments because we know the semantics of the system calls. like a file descriptor number and address of the calls to connect or something like that.
So you don't have a notion of causality between events on different
We
processes?
don't use that information.
Because that seems pretty fundamental to debugging concurrent systems.
Yeah,
I mean,
yeah.
If you can't establish some causality, then it seems like there's a certain class of
Yeah, that's a very good question. Actually, the most of the work on similar work uses the correlation between remote machines.
Right.
And of course, I first thought about that direction, but the question is how to do that for, say, thousands of machines. And I try to do localization without using correlation information because for the sake of scalability. And the part of the goal of this research is what can be done without correlations. Actually, in my previous experience, some of the difficult bugs is actually it manifests to the multiple machines, but it also has some different. It also has manifestation to the local process. So I talked about how to model the system, and then we use this model to localize particular failures. So it's very similar to the model of this derivation phase. It first collect failure trace. We always collect the system function called traces, and decompose the trace into units, just like the model derivation. And for each unit in the failure trace, we quantify how different from the model, and assign a score to each unit. We call it a suspect score. Then we report the result to the human administrator or developer, and so that she can prioritize the highly suspected part of the execution, instead of just need to looking at all the execution histories with no clues. So the suspect score is to, as I said, is to quantify how different from the process, the behavior, compared to the normal behavior. So we want to assign a high score if the high probability function wasn't called, or if the low probability function was actually called, we want to assign high score. So these are the motivating heuristics of our modeling. And so to do that, we do assign score like this. So if some function was actually called at the time of failure, we assign the score 1 minus p. P is the estimated probability. But if it's not called, we assign just the same value of the probability. So let's assume the probability was 0.9. So it means most of the time it was called. But then it's called. And then we give just 0.1. So it's relatively small. But it wasn't called. We give 0.9. It's much greater than it was called. So we do this to realize these heuristics. So we do this for each call in the unit, and we take the average of this score for the as the total score of the unit. And we do this analysis for every unit we found in the corrected faded trace. And then usually then create a graph or visualize the score with a timestamp of the with the traces.
So your model kind of breaks up each process into different contextual units.
Yes.
In your failure trace, how do you know which unit to compare?
Sorry.
How do you tell the context in your failure traces? How do you know which of those can be used to compare?
Yeah. So the question is how to match the particular units to the model. Okay. So we do this just like the grouping of the units in the model derivation phase. We looked at what's the call stacks to the connection that particular unit had a message from. So that's essentially the same with this phase. We find the units with the same call stacks to connect or other connection establishment functions.
So you assume that you have enough normal traces to cover all the possible contexts?
No, I don't.
What if there are missing steps? What if in your failure traces you see many steps?
In that case, we assign the maximum score because that should be analyzed by developers because in the normal run that connection has not appeared, right? So that should be of interest for developers or system administrators. So if we don't find the matching model, we assign the maximum score for that should be of interest for the developers. So we apply this modeling and localization to the bag I had introduced at the beginning of this talk. It was caused by missing return value check to a receive system call. Has not appeared for a long time, but appeared if used with multiple sites with a large number of nodes. And I would say the error handling was very naive. It just closes the network connection but doesn't terminate the system. So the user, so it's very troublesome if you run long-running parallel programs. You submit the parallel program, then usually large-scale program, a program itself takes time. So the user don't know whether it actually his computation was actually starting or whether it was just computing his application. So Hideo Saito, he's a friend of mine, discovered the bug, as I said before. We wanted to show how effective our technique for this bug. So these are so to try to take traces from a system, we use some standard techniques like library interpositioning. We use this interpositioning to take a trace of system calls. Also, we use as a compiler and one-time provided function called fux. We use, in particular, we use GCC's the option for the compile time function fix. For the other, also, this MPD is implemented with a Python script. It's relatively large script, and we do this. We do tracing of Python scripts by the standard debugging interface of the Python runtime. So essentially, we don't need to modify the application program itself, but sometimes we need to recompiling the system. We can do this without recompiling if we use some binary translator, but we haven't do that not yet. So to create a model, we take normal traces by running the MPD just using a single cluster. It works with no problem. We take traces on this system, then create a model as I talked before. Then we run the same system by using 78 nodes distributed over 3 sites. So in this case, the number of nodes was around 32, and we create a model with this system configuration, and then compare the model with the failure traces we collected from this configuration. So before presenting our results, this is overhead of a function called traces. So each bar represents performance overhead of MPI programs. It's actually very low, something very negligible, and at most 7%. That's because we don't trace these applications themselves, but we only trace the middleware, the MPD, to manage these jobs. If we had traced these applications too, probably the overhead is much larger. But for the scientific programs, we don't want to impose overhead much, so we just take traces of the underlying middleware. And if we did so, the overhead was not much, and it's actually negligible.
So you're saying that function traces, but stack traces are only for the middleware,
Yes.
not for the full application?
Yes. So this is visualized results of the suspect score calculation. So the x-axis corresponds to the timestamp, the time of from the beginning of the execution. We had about 17 seconds of run. We start the system here, and then because the MPD looks hanging up somewhere, we stop the execution about just after 70 seconds. The y-axis corresponds to the score of the unit observed in particular elapsed time. So we see the high score units at the beginning and the final stage of the execution. So when we looked at this, in this case, it actually has is actually caused by closing a connection, and this duration system was just hanging up, and the high score of the last minute was due to the not standard system termination.
I'm sorry, is there a tremendous amount of overplotting going on there at the line at the bottom, the line at the bottom?
Yeah.
I mean, how many points are represented altogether in the data set?
Here we have only 1 point.
Right,
But
I'm thinking at the bottom it looks like
yeah, there are many points actually plotted to the same timestamp, same time.
right. So how large? I mean, I can't tell visually how large the whole data set is.
Uh,
So they're all together, you know.
I don't remember particular numbers, but I can look at the numbers later.
I'm just thinking in terms of the distribution. I guess most of the math it visually looks down there, but is it even more extreme because of the overplotting?
Uh-huh.
How
Actually,
special are these outliers?
I remember actually most of the units are located here, and then the system was dormant after the initial the problem right here. So the each process wasn't that active, waiting some message on the select system call, then take having timeouts, then again waiting incoming message on the select system call. So the process wasn't that active, so we don't have much traces on this duration.
So have you done, you explained one case study, the MTV case study, right?
Mm-hmm.
And have you done any other case studies?
Not yet. I'm currently working on to do the same analysis for other distributed file system middleware, but I haven't got any results yet.
So what I'm not able to get is, it seems that a lot of your analysis
Mhm.
was motivated by MPD,
Mm-hmm.
right? You have a certain method of building models that was motivated by the MPD experience. I want to know how general this is in other cases. Is it likely to find
Sure,
bugs in other
yeah.
cases also?
Yeah, that's a good question. Of course, I want to try to localize as a fault, but one of the difficulties to actually has experience to work with real problems in the real world environment. I was actually lucky to have the opportunity to work with this problem. As I said before, there are many large-scale failures in the usual, but for the real problems, it's usually hidden into as a company secret or some particular environment. It wasn't published. It wasn't made publicly available. So the problem is it's really difficult to have the experience with real world problems. But I believe this kind of modeling to detect rare function call behavior is useful for example, we had a problem in the Tokyo Stock Exchange last week, and it was due to a missing call to initialization of particular data structure. In that case,
So how do you know that?
it's reported in the news site.
Okay.
Yeah, and if I could apply my technique to that problem, probably I could see some high score for the
Okay.
I initialize the data structure. And also, in my previous experience, I worked on with other students on the failures in a cluster, and we developed a different techniques for that particular problem. In that research, I also observed a problem that manifests the problem itself to other defined function calling behavior. For example, when this is one of the failure was due to failure in the network connection between two nodes in the system, and then it tried to send a message to the nodes, but it wasn't successful. So it falls back to some different path because of the failure. In that case, we see a difference between normal execution and failed execution. And we can spot at where the system starts behaving differently. And I believe the function calls can provide fine-grained information for diagnosing the system. We are not saying this can provide this can answer the two root cause of the failure by only this technique. We can direct the developers to where to look at first and where to look at to find the real reason of the system. And I think function call behavior, function calls is very useful information for developers.
Okay. So would it be possible to build like a fault injection system to perform a more comprehensive evaluation of the techniques?
Fault injection
Well, to essentially synthetically inject the faults.
To test the effectiveness of our technique? Yeah. I would say so. I would think it's possible. That's one of the possible directions to evaluate the effectiveness of this type of research. But the challenge to successfully evaluate the system by fault injection is to what's the fault to inject. If you know the faults, it's easier to develop a model. But only with fault injection, you can't say much about the generality of the technique, because.
You can say a little bit more about it. Right?
Sure. Yeah. So before concluding this talk, I would introduce some related work. There are a large number of research projects to do similar analysis for localizing system failures. As you said at the beginning of this talk, most of them try to reconstruct the distributed flows, find the correlation with each behaviors by recording the message sending and receiving events. And then, so this is a simple example of the how this research project works. So the blue line represents a succeeded request. So we have, in this case, the request from this computer successfully returned to the requester, but on the red line case, due to some problem in this node, the request failed. So many related work tried to find this distributed flows across the node boundaries, and then compare the successful flows with the failed flows. So for example, we can discover something like many failed flows visit a particular node or a particular URL. And then we can tell developers to suggest developers to look at particular URL for more further analysis of the failure. This kind of technique actually works for many problems, but the question is what's the scalability of this analysis, of this discovering distributed flows among, for example, thousands of processors. So I started this project how to do localization without this kind of correlation information, so that we don't have limitations with the scalability with the number of included processors or machines. So let's conclude my work. So we have worked on fault localization for the large-scale machines. This technique creates a model to describe the normal behaviors with a function called tracing to create a model. Then we use the model to detect anomalous behaviors by comparing with the traces collected as the failed ones. Then we had a preliminary result to show the effectiveness, and we are currently working, as I said before, we are currently working on to applying to other system. That's a distributed file system for clusters and grids, and I contacted the main developer of the system, and he seems to have lots of example of how to discover failures, how to discover the cause of the failure. So I'm currently trying to apply this modeling to the system, or more can be or trying to the system can be more general. So thanks for listening to my talk.
Any other questions?
I don't have a question, but I do have a comment to one of the questions earlier, which is that tailoring one's approach to one example might seem like not so generalizable thing to do, but given this area is just starting out, and there have been no extensive studies of what kind of faults occur out there on all kinds of different systems,
Mm-hmm.
and no publicly available data sets or publicly accepted evaluation metrics, that makes it really hard to design a general system. And like even having one example of this in the real world is already very difficult, I think.
Yeah.
And that's why working, potentially getting access to the data here at Microsoft or other big corporations by actually going there and working there, it would be a really
Yeah.
valuable experience.
Yeah.
Something that you can get.
Yeah. That's one of the motivation that I I would like to work for here. Yeah, the real world. Yeah, real world challenge is my getting real world access is the biggest difficulty in this kind of research. So my another work is at my another work I do different photo localization with other students, and we applied the technique to computing center of our university. The center has a cluster that actually used by application programmers in the Tokyo Institute of Technology, and it's a real production service. So we had long time to persuade why our technique is used for the system, and we take tremendous amount of time to show the stability of our technique, so that it doesn't affect adversely to the system. And we successfully applied the technique, and we got some results. And we could review some very difficult case of the localization, cause of the falls, and it was a really unique experience for me. We don't just need to work on a specific technique, but we need to make it more robust for applying to the real world environment. And but but after that, I feel it's very rewarding work because of the scale of the research application to the real world environment. So I'd like to work for the problem that I would say that I guess Microsoft can provide to the researchers here.